Good afternoon, everyone. Thank you for your time and attention. Thank you for this opportunity. My name is Vishal Patel. I'm a general surgery resident here at the University of Washington and a biodesign fellow at UCSF. What we're going to talk about today is one of our innovations from basically the Innovations Engineering Lab over there, which is going to be an implantable microsensor which can communicate wirelessly to ensure safe coupling of our magnetic rings. So I have no financial disclosures. We will, however, be discussing MagneMosis, which is a Class 2 FDA device with an IDE, but not on the market, and the following is all patented. So in a brief outline, first we'll talk about MagneMosis and our promise of magnetic compression anastomoses, this technology, and where we hope it will lead in the future. So it all starts with MagneMosis. This is a magnetic compression anastomotic device, 23 millimeter rings. They are encased in polycarbonate and completely biologically inert. These rings will self-align due to the magnetic field, snap together, and actually create an anastomosis over a period of 4 to 5 days. The key here is the geometry, where the center of the rings actually have a very high pressure area which causes tissue necrosis and death. And at the periphery, it exponentially drops off and actually creates a pretty good milieu to cause scar tissue formation and wound healing. So far, we've been successful in 8 humans, over 90 pigs, and a number of monkeys as well. So far, successfully, we've done it in gastrojejunostomies, small bowel anastomoses, colonic anastomoses, and even small bowel colonic anastomoses. In all of our studies, what's been incredible is that we've had 0 instances of an anastomotic leak, and the anastomotic strength is actually equivalent to hand suture and significantly better than staples. So initially, the natural place to start is open surgery. We just finished a clinical trial in 5 patients who are receiving ileal conduits, and we successfully created an anastomosis in all these patients using MagneMosis. Over here, you can see that the magnet's in the right lower quadrant immediately post-op, and over a period of about 2 weeks, it goes through the colon, makes its way down to the rectum, and is eventually excreted uneventfully. But that's open surgery. There are a number of indications where we want to do things less invasively, and I think the promise of this is going to be a completely endoscopic or NOTES approach to us actually creating a bowel anastomosis. So this is one case recently at UCSF in a patient who had a small bowel obstruction, child C cirrhotic, and unable to be an operative candidate. Using endoscopy, we ended up introducing 2 magnets and bypassing that small bowel obstruction. We ran into a number of challenges in this procedure. Namely, we didn't know exactly where these magnets were outside of fluoro or when they actually hooked up. And when it hooks up, we don't know if there's bowel or omentum or other tissue that's in between, and that can lead to a devastating complication. So that leads us to our key challenge. We want to get purely endoscopic with this. How do we get there? And how do we know if these rings are actually mated and exactly where they are in their body and if they're progressing along where we expected? So we have some criteria to actually have a successful innovation here. It has to be integrated in our polycarbonate coating and biologically inert. These magnets have to tell us and be sure that there's no structures in between, and the surgeon needs to be able to know this wirelessly external to the body. And after the initial operative period, we'll follow these magnets through, and using an external reader at the patient's bedside, we should be able to make sure that they're still mated and exactly where they are. So this leads us to trying to solve this with engineering. We used a printed circuit board. This is actually remarkably thin. It's only about 1.5 millimeters thick, and it has a number of valuable tools on it. First is an accelerometer and a temperature sensor, which can tell us in any 3 axes exactly where we are and what's the orientation. Radio frequency module to communicate with the outside world, a microcontroller to integrate everything, and then some electrical engineering components to actually convert our signal and boost the signal so we can read it outside the body from such a small package. Integrating it structurally was actually the simple part. We created a modular design where the 4 sensors are essentially sandwiched around our printed circuit board and an antenna, and all encased in the polycarbonate. The tricky thing then becomes, all right, how do we measure a force inside this device, and how do we figure it out outside, and how do we understand what it is outside? So it starts with measuring it, translating what we're measuring, communicating with the outside world, providing power to this device without any battery source, and then understanding what's actually coming out. So we start with a force-sensitive resistor, and this is basically a gated channel where if there's no force, the gate is completely closed. As a force is applied to this from the 2 magnets or bowel essentially pushing on each other, the channel slowly creaks open and allows the flow of current and electrons through. And as that happens, the resistance lowers in that circuit. So now we know that the resistance is lower, but what do we translate that into something actionable? So we use this Schmidt trigger oscillator. And what that basically tells us is that when the force increases, the resistance decreases, and the frequency that we're going to read actually increases. So at baseline, it's a kind of a base, a natural sine wave frequency with no force applied, and that frequency changes by X amount whenever there's a specific force applied to it. Now we have to power this device because it can't read, it can't speak on its own. And our solution here is something called inductive power transfer. And we're all familiar with this, whether it's electric toothbrushes or putting our phone on a charging mat, which actually provides power to that device. And the principle here is that there's a magnetic current that we put in the outside device, which then, magnetic field that we change in the outside device, which then generates a current. This current, when close enough in proximity to the internal magnet, will actually transfer that current over there, which then powers the entire system. So the external coil and a signal results in a current for the internal coil. Now we have power in that system, and we have a frequency, but now that frequency has to talk to the outside world. So as the force sensor changes the resistance, the frequency, inherent frequency changes. We apply an external frequency which then interacts with what the device is telling us. And by measuring these small changes, we can actually understand exactly what the changes in the frequency are. And then just kind of completing the whole circuit here, I guess, there's two ways. One is the whole electrical circuit and communication is complete, but also us trying to bring engineering solutions back to the bedside. So once we measure it, we translate it, we power it, it talks to us outside. And then there's some back-end computing using a Fourier transformation, which actually converts a frequency into a force. So it kind of comes full circle through multiple little breakpoints along the way. And in the end, for the surgeon, all it tells us really, what we want it to tell us is a green light or a red light. Is it stop or go? Are these magnets hooked up? Are we confident that there's nothing intervening? And if we are, then we can safely say endoscopically, even with a fluoro shot of the patient, that we can feel pretty comfortable that there's nothing in between here. So this technology, of course, has a number of uses, and I think our novel approach here was to say, can we implant something in the human body which has good mechanical or physiological monitoring benefits, and can we have that without a battery that can talk to the outside world with us at the bedside and actually try and understand the solution? So we think we've accomplished that. So there's a number of uses, whether it's going to be continuous glucose sensors or continuous EEG, which are already out there. People trying to do continuous physiological monitoring or brain monitoring, and even these wild ideas that you've heard of wireless body networks where they can integrate multiple different physiologic parameters. Almost all of them are going to speak through RFID and be powered through inductive sensing. There's a number of challenges, whether it's heat or miniaturizing the packaging, or even challenges with the frequency. So thank you. Any questions?